We have snakes, we have armadillos. Let's extend our zoo with ants. Each ant is going to have a weight in pounds, and it's going to have a location in the zoo which will represent as a posin, sort of Salt Lake City style, relative to the ant's home, which will be at the origin. So, for example, that means an ant has two parts, a weight and a location. We'll need to say an ant is make ant, a number and a posin, where we introduce make ant through this define struct ant. Weight loc will be the name of the field, so loc is short for location there. For example, make ant 0.001, make posin 45, that is an ant that is 0.001 pounds and is 4 and 5 away from its home, and this is an ant that's 7 times as big and even further away from home. You can think of this make ant 0.001 make posin 45. That is a value, because make ant is a value when either of its parts is when both of its parts are a value. This number is a value, and this make posin is also a value since its parts are values. In other words, if we're in Dr. Racket and we type make ant 0.001, we got too many zeros there, make posin 34, we just get back make ant 0.001 make posin 34. Can't be simplified any further. Or you can think of it in this box form, where an ant has two slots. An ant box has two slots. It's just that in one of those slots we put another box, which is a posin, which also has two slots. These boxes, of course, can stretch to be as big as they need to for whatever you put in, even big enough to accommodate another box. So with that data analysis done, we've sort of decided how to represent ants for all of our various ant programs. We can consider a specific function, such as ant at home. It's going to take an ant and tell us true if the ant is at the origin, false if not. So as our data analysis said, ant at home is going to take an ant, where an ant is make ant, and it's going to return a Boolean true or false. So it checks whether the ant A is home, and there's our header, ant at home A. We can make some examples. We need an example where the ant is at home at the origin, an example where the ant is not at home because it's at 1, 1. So that's where our examples produce true and false. Given those examples, what's the next step in the recipe? It's the template step, where we ask the question, is the argument A compound data? And we'd have to go look at the ant data definition that says an ant is make ant. This data definition would be probably earlier in the file, but we'll just put it here for a moment. Yeah, I see make hyphen. It's compound data. And the two pieces, it's got two pieces, a number and a posin, so we need to pull those out. We look at the define struct, so we know it's ant weight and ant location that pulls those out. Now, you may notice, of course, a posin has two pieces inside of it also, but we don't see that immediately in this data definition. What we see in this data definition is a reference to a posin data type. So what we're going to do is not pull that posin apart, but instead assume that there will be some other function that will handle these complex things, these posins. Right? So this is a new part of the template, which is that when your data definition refers to another data definition, so here I have an ant that refers to another data definition, not written here, that is a posin, then we want the template to refer to another template, or ultimately the function refers to another function. Right? So that's why we still have two parts in our template, because the compound data had two immediate parts, and we have this reference to this other template. And the way we handle that other template is, well, it takes a posin. Is posin compound data? Yes. And so we pull out the two pieces there. And then when you finish up the whole program, it'll look something like this. There's the templates intact. We discover that the ant weight is not really relevant, so ant at home is just checking whether posin's at home, and there is posin at home. Okay. So what you see when we get to the end is that we had these data definitions, ant and posin, and we ended up with programs, in particular templates, and then the programs derived from the template, that match the shape of that data. It looks obvious in this case, but as we go, this concept of making the program match the shape of the data definition is going to be crucial to writing programs that work.